All right, it is noon, 12 o'clock. Welcome to lecture, is it lecture 13? I believe so, lecture 13 in Comporg and TGIF. It's Friday again. Looks like it's raining, so hopefully you enjoy being in the lecture. All right, so let's get started. How folks you are doing? Doing good, but still working on the homework. Hey, this Webex update is gross. Yeah, it looks quite different. So yeah, I also noticed algo exam. Yeah, I know it's that time of the semester. All right, so let's get started. Hopefully, all our panelists for today are in and answering questions. I see some of them are answering. Yeah, there's like a vote for the favorite MIPS register. Okay, let me start sharing something, and then we will get started. Poll number one seems important. You notice, huh? Yes. So I heard from several students that they would appreciate an extension on homework because it turned out to be harder. That is than they expected. That is one reason, and the other reason is we actually had a submit issue which didn't affect that many people, but it still affected some students, and so for those students, there might be a delay associated with submitting being not available to grade their homework 3. So that's why I thought an extension might be appropriate, but then I realized that we might have students who, kind of stayed all night trying to finish by yesterday, by the end of the day yesterday. They might be unhappy if we now extend the deadline. So that's why we have the vote. Okay, so I will just go with a majority vote. How you people vote, I will just go with that. Okay, so yes, that's our first poll for today, and let's. Yeah, it's open circuits time. Exactly. Have you heard about open circuits before, or are you one of the developers? Yes, if the deadline gets extended, it means that all late day usage will be recomputed by submitting. Okay, yeah, we'll talk about open circuits when we get to gates and actual circuits. All right. So what we need to talk about, let's start. First, half semester mark. I believe it is the last lecture of the first half of the semester. Officially on Tuesday, we will start our second half of the semester. So among other things, that means that people who were helping other students on Submiti Forum, I will gather, so sometime over the weekend or maybe on Monday, I will gather submitted statistics about the forum usage, and I will look at the people who were most productive, and I will look, of course, into their posts to make sure that it's not just asking questions, it is actually answering, attempting to help other students, whether and whether their answers were exactly correct or half correct is of lesser importance. It is important that people were trying their best to help, and those people will receive extra credit for submitting forum participation, as we agreed to do in the beginning of the semester. And then we will do the same kind of stuff at the very end of the semester. So if you haven't been active on the Submiti forum, you can still get some extra credit for that. You still have the semester to go. Okay, so did we get through all chapter 2 slides? Yes. Yes, we did. So we are starting chapter 3A, which is, if you look in your textbook, is not really chapter 3. It is actually appendix B, and we will start with that material today. And homework 3, so we already decided it is going to be due tonight. Well, no, we didn't decide. All right, so there's the vote. Okay, so I will look at the vote outcome after the lecture or during my office hours, which are pretty much after the lecture, starting at 2:30, so that I have enough time to actually get from home to campus, and then I will make the decision. So if you depend on if it's important for you whether we end up moving the deadline or not, please monitor, please check submittee. When the decision is made, I will just move their deadline on submitting. That's how you know if the deadline got moved or not. And I will make the outcome of the voting available to you, so you will actually see how many people voted for, how many people voted against, and how many people didn't, abstained. Homework 4 will be mostly on the new material, Boolean logic, gates, circuits, and all that kind of stuff. And it will be released over the weekend. I actually have most of it already written. I just need to proofread and double check and solve it myself to make sure that it is solvable. And then I will release it. So hopefully it happens tomorrow. I know some of you asked me to release their homework on Fridays, and I was honestly trying to do that, but I don't think I will be ready to release homework for today. So over the weekend, hopefully on Saturday. Is homework 4 code-based or LaTeX-based? So there will definitely be textbook style problems. They're probably not going to be from their textbook, but they will be, that kind of style where you have to type your answers and put them in the PDF, make them into the PDF. Whether there is a coding part or not, I'm still thinking about it. So I haven't decided. You shall see once their homework is out. You will see. Well, we have to go with some textbook problems as well, right? Because you might not like them, but there are people who hate coding questions, right? So I've heard this before from some students. Oh, just please no MIPS, no more MIPS coding. And then similarly, I've heard from some people, oh please no more C coding, no more malloc and all that kind of stuff. So. Yeah, sorry, I don't have any good news for those of you who would like some of the major topics in our course to never appear again. It's very unlikely. Sorry, not much I can do. Yeah, MIPS is not going away. It's going to stay with us until pretty much the last lecture. So. All right, and then exam 3 grading. We are over 50% done, so our TAs and mentors are working on that. So just bear with us. They are doing everything they can. Their average grade looks pretty decent so far, because as you know, we made problem 6 extra credits, so their whole exam is out of 80 points now, and that of course helped. So the average is actually looking better than on exam 2. Okay, so lab 4 was this week, so hopefully you liked it. But please feel free to share what you think about lab 4. As usual, solutions will be posted on Monday, but you should have by now you should have your own solutions. So the only reason we post solutions is just to give you maybe another way of looking at the problem. So look at our solutions and see maybe maybe your solution was correct, but maybe it was different. So you can get exposure to different ways of solving the same problem. Okay. Someone says multiplication homework 3 not so much fun. Well, I have maybe bad news for you if you don't like multiplication. So we are going to have more multiplication and division because we will look at computer arithmetic much closer. And this actually starts now. Starts very slow with primitive gates, but it will get to the actual hardware that performs your addition, subtraction, multiplication, and all that kind of stuff. And it gets pretty complicated. So, just a heads up, we have to look into that. That's really what a computer is, right? You think a computer is something that that you can play games with or can play games at, and the answer is yes, maybe, but the real thing is, computers do really compute. So if you are a computer scientist, or a computer science major, you need to know how computers actually compute, how they do, those addition, subtraction, multiplication, and that kind of stuff. So that's one of the big things that we need to do in this course, and that's why it is coming. All right. And we have slides for today, a whole bunch of them. And yes, we will be using open circuits, but I will get to that when we get to our first logic gate, right? So just a bunch of slides for today. Hopefully, say yay, and the rest of the month, probably more slides. So coming up, just a lot of material. It's very dense, and we have to go through that fairly quickly to get back on track. But we are more or less on track. I just checked with the notes from last semester when this course was taught by another instructor, and we are actually just half a lecture behind. Okay, so not by much. So, and if you look at their schedule, you get an impression that we are a lot behind, but they were a lot behind in the last semester. So that, I guess, that's kind of normal. All right. So we are good. Don't worry about that. All right. So without further ado, and yeah, if we have time at the end of the lecture, please remind me. So I got a request, so to speak, from our TAs and mentors, or an observation from them, saying that many students are still struggling with RA register and the whole concept of calling the procedure with this storing the return address in RA and then taking this value and using it to return to the caller, and in general with a stack pointer and saving stuff on stack. And of course, this is something that you need for homework 3. So if you're still working on that homework, that might be helpful. So if we have time, I will ask you to ask questions, and I can explain that topic again a little bit more. Okay. So, and like I said, the material that we are starting now is really Appendix B, and then we'll get to Chapter 3. All right, so it's kind of blended together here. All right. And we will be talking about Boolean algebra. So what is Boolean algebra? Well, it's like your regular algebra with letters that stand for variables, and variables are just placeholders for values. So if you think about it, they are like variables in a programming language, those letters, those identifiers. And Boolean algebra is just a set of rules that are based on the theory developed by George Boole in mid 19th century. And because it's the name of the person, Boole, so we spell Boolean algebra with a capital B. Okay, so that's the correct way of doing that, right? Because it's a proper name. All right, so it's basically a mathematical theory of logic, where logic is really simple because it only has two values, true or false. And then there are multiple uses of Boolean algebra, and Claude Shannon, another very notable person in the history of computer science and informatics. So Claude Shannon was responsible for actually defining what information is, and giving the first official definition of information, and building the whole information theory around that. So, and that was already in the 20th century. So Boolean algebra is extremely important. Okay, and the funny thing is, so in the past, I had students who were trying to do Boolean algebra using Minecraft. So that was pretty amazing. That was pretty creative, and they were trying to even. So one of their assignments later will be to actually, for you to build their ALU, arithmetic and logic unit, which can do addition, subtraction, multiplication, that kind of stuff. And some people were trying to do it in Minecraft. And they didn't get too far, so I think they implemented a subset of operations that were required, but that was pretty amazing, right? So if if you're doing if you feel like doing something like that, knock yourself out. Okay. So what do we have? Well, we have values that can only hold two things. And it doesn't matter what we call these two things. We can call them true or false, or 1 and 0. And, we can actually map them to other physical quantities like voltages. So we can say 0 is 0 volts, 1 is 5 volts, or true is 5 volts. So that, of course, make it very convenient to implement all the things that we are going to talk about now in real hardware, right? So it can be directly linked to electrical engineering or digital circuits engineering, and that's why it is very popular. Do not, however, assume that 0 is always 0 volts, right? So this connection can be actually exactly the opposite, right? So it's important to see the distinction between Boolean algebra, which is just a theory, and its actual implementations, let's say in electrical circuits. Okay, so you can totally create an electrical circuit where false or logical 0 would be represented as 5 volts, and false or logical uh, and true or logical 1 would be represented as 0 volts, right? There are actually there are circuits that do exactly that, and there are reasons behind that. We're not going to go explaining that, because it's really more of computer and electrical engineering stuff than computer science. But it's important to see this distinction. So true or false, or 1 and 0, are purely logical values. Okay, and yeah, there's a joke like this logical something is a fairly known is a fairly known joke, because when you say logical 0, it may mean not 0 at all. Like logical 0 in an electrical circuit can correspond to 5 volts. So go figure, and that's why. When we have occasionally, because of the holidays at RPI, we have Tuesday that follows Monday schedule or something like that. So I would call it like it's Tuesday, but it's a logical Monday, right? Because we can have this distinction, between the physical day, like Tuesday, and the logical day that RPI wants us to treat that day as something else, as Monday. All right, so there are several operations that we can perform on Boolean values. And of course, operations have a number of arguments. So the number of arguments can be 1, 2, and more. And we are mostly concerned with operations that either take 1 or 2 arguments. So there's only one operation that takes 1 argument, obviously, and this is a not. So not is negating the value. It is flipping the value. So if the value were true, then not that value would be false. Okay, and this is denoted as an overbar. So it's Boolean algebra, and we deal with letters. Okay, so letters, they are placeholders for values, right? So we have letter A that can be true or false. We can do some transformations just with letters. Okay, same as with your traditional middle school algebra, right? You don't know what A and B are. If you want to perform certain transformations, algebraic transformations, you can do that. Of course, if you want then to evaluate the expression, you need to know the values, but you don't need to know the values to perform transformations. So the same idea carries over to Boolean algebra, right? So this overbar stands for not, and as you could probably guess, it is not very convenient to write if you can only use ASCII. All right, where is my pen? Just bear with me, please. Check what happened to my tablet. So I want a drawer, but it's not. It got unplugged. Okay, I got it back. Right. So you cannot really draw this overbar if you just use an ASCII, like if you're writing a text file. Of course, in the homework, if you're using LaTeX, this overbar is very easy to do. So please do the overbar. It is the easiest and the most visual way to indicate a negation. But alternatives, if you are only limited to ASCII, would be exclamation and tilde. Right. So those are alternative ways to indicate not. Oops. All right. So, and yeah, you can use this notation in text files. It is fine. Okay, it's really up to you. But if you're typing homework in Word or LaTeX, then please use the overbar. It is easier. And the reason why it is easier, because like if you have an expression, something like this, right? So this notation clearly tells you that, oh, I need to do A or B and then negate the result. If you're using the notation with an exclamation or a tilde, it's harder because here you have to use parentheses, right? Because if you don't use parentheses and you write something like that, okay, so there not is a unary operation, so it binds with the closest letter. So this is really, if we write it using our overbar notation, this is that, okay, and not what we originally had, not this. So please be careful. Make sure you use parens as in regular algebra, okay, but even more so if you're using exclamation or tilde instead of the overbar. All right, so and then among binary operations, and we discussed before, so there was a poll on the number of binary operations. And by the way, yeah, remind me at the end of the lecture, we can go over recent polls. I think we didn't go over them, so let's go over them and discuss what the correct answers were. And so one of the polls was how many Boolean functions we have. All right, just given n, the number of arguments, how many Boolean functions we can have, and and the answer was 2 to the power of 2 to the power of n. Okay, and when n is 2, so it's 2 to the power of 4, 16. So there are 16 Boolean functions of 2 arguments, and we are, some of them are more interesting than others. As it turns out, there is something that we will call a functionally complete basis. So we are typically interested in a subset of those binary of those Boolean functions, and that's and we start with just 2, or and and. Okay, and for or we use the plus sign. You can also use a vertical bar because this is or in some programming languages, so you can use that as well. And probably the preferred would be 2 vertical bars, because in programming languages there is a difference between the logical operation and the bitwise operation, and therefore, typically their logical would be the double character, like the double vertical bar or the double ampersand. And but this is, this is less preferred in our course. We would still understand it. We would not deduct for this, but this is more like a programming language thing, right? So here in the Boolean algebra, we prefer to use the notation either plus, or there is another notation that looks like that. Okay, so this is called disjunction, and it's just a fancy word for or. Okay, so this, it looks like a V or a big V, but this is an operation character. So you can use the plus, or you can use this disjunction character. And for and, they're preferred. So plus or disjunction, you can use either. They are both good, right? And like I said, they're 2 vertical bars. It's okay, but definitely not the preferred way when we talk about Boolean algebra. So for and, it is a dot, which looks like a multiplication, right? And or looks like an addition, but we will talk about it why or does not really perform addition, or the addition that we would like to have. Okay, so addition is not as simple as just oring two arguments. So back to AND. AND is the dot, or you can use this V rotated 180 degrees. So this is called conjunction. Okay, so that's again a fancy name for an AND. And you can, like similarly to the or, you can use double ampersand for and, but like I said, it would not be the preferred way of doing things. All right, so that's the basics. That's the notation. And then let's go over operators. We've talked about them before. So, a couple lectures ago, we looked at the truth tables of or, and, not, and even another operation called exclusive or XOR. So that stuff should be familiar to you already. So the result of or is 1 if any of their two operands is a 1. So or is similar to addition, but operates on binary values. Well, we will see that it's important to say that it is similar, but it is really not the addition. Okay, and we will see an example that shows why. All right, and it was actually in the notes in the lectures a few lectures ago. All right, so and is 1 only when both operands are ones or both operands are true. And it's important to see here that and is a function. Okay, it's a function of two arguments. So we supply two arguments to inputs, and then this function and or whatever computes the result. As any function, and or it's just a mapping, right? So you map inputs into their input values into the output values. You map input values that are drawn from what is called domain into their range. Okay, and for Boolean functions, everything is easy. Their range, the domain is only true and false. We only have two values, and the range is the same, true and false. Okay, so basically we are mapping. So if we represent this, any generic function using a more math-like notation, so we have a set of two values, true and false. Okay, and then we actually have two arguments for and, or, and other binary Boolean functions. Okay, so this is our domain. And the function maps that domain, and note it maps in there only in one direction. So it is not necessarily reversible into T and F. And this is the range. Okay. So, TF, two sets multiplied, that would give us, the values like TT, TF, F, T, F, F, and on. So close to the bottom, like that. Okay. So that's just the product of two sets, right? Just all possible combinations. All right. Yeah, they brought back domain and range from 7th grade math. Imagine 7th grade, and that stuff is still useful. That stuff still comes up. All right. So not very easy, just negation, right? We would sometimes say negation because not negates its operand. We would sometimes say invert, right? Because it inverts, right? When we only have two values, when you flip or invert the value, you go back, you go to the other value because there's only two of them. So all of those terms would refer to the not operation. All right. And of course, algebra would be boring if we couldn't do equations and formulas and expressions. So we can combine letters that stand for Boolean values with all the operations that we just talked about. And for now, we will limit our set of operations to and, or, and not, but because they actually, it turns out, and I'm not going to prove it right now, but so please take my word for it. So you can express anything with a set of three, with this set of three operations, and that's why it is called a functionally complete basis. And then we will learn that there are other sets of Boolean operations that also form functionally complete sets or bases. Okay, so that's why we are limiting ourselves to just these three: and, or, and not. All right, so here's an example of an expression, and if we have two expressions with their equal sign or not equal, that would be an equation, right? Good news is you cannot really, since we only have two values, you cannot do less than, right? So for Boolean algebra, we do not compare the values for less than or greater than. There is no ordering in the set of values for Boolean algebra. Unlike with our number line, right, where we could, our number line, our integers, our real numbers, they are ordered, not like Boolean values. So, something is easier here than with natural numbers or integer numbers or real numbers. All right, so that's that, and here is a bunch of examples, and we can evaluate certain expressions if we know their values for each of the variables, or if their expression contains our constants, our literals. So true and false, so 0 and 1 are our constants in the Boolean algebra. And so we just perform this. This is an OR. So 0 plus 1, 0 or 1 is 1. 1 and 1 is 1. So we can evaluate it to 1. Okay. So, doing things like that, we can you help me with x2? What is x2? Is A, why is it A? Because it's the law of excluded middle. Okay, yeah, good. So the observation here is, well, there are certain things that we can observe if we try just the substitution. So imagine A is 1, then we have 1 and 0, okay? And so it's a plus, so it's an OR. 1 or 0 is 1, okay? And then what if we say, well, maybe we just got lucky. What if A were 0? We can say, well, if A is 0, then not A is 1, and the result is still 1. So it turns out that no matter how you slice it, the result is 1, all right, irrespective of what A is. And of course, we would be tempted to say, well, such things, such observations, we want to make into lures so that we can actually use them, okay? And x3, we can do the same thing. So if A is 0, well, we don't even have to compute not A because we know it's going to be 0. If A is 1, well, we are not sure, right? Because we have to check the other argument. Not A is 0, and we know that it is 0. Okay, so we conclude that this is always 0. All right, what about x4 plus 1? And plus, remember, stands for or. It is 1, okay? Because with an or, if one operand is 1, or yields 1, regardless of what the other argument is, okay? Here it's funny, right? We just computed the right-hand side, and with now we have to look at, oh wait, but there are equal sign. So for the first three, it's pretty straightforward. We say x1 is going to be 1, x2 is going to be 1, x3 is going to be 0. We computed them. But, x4 is 1, turns out, okay? So that's kind of mind bogging, because like, oh, but what if x4 had 0 initially? 0 or 1 would still be 1, and then we kind of assign 1 to x4, okay? So, be careful with formulas that have their, the same value, on the right hand side and on the left hand side, okay? All right, so now let's talk about laws of Boolean algebra. For the most part, we're not gonna care with proofs. So as someone mentioned, you have forks for that purpose. Okay, where you do tons of proofs. Hopefully you love it, but we're just gonna use the results of those proofs. So let's go over Boolean algebra laws. So like with any other algebra, it's just a set of postulates and identities. So basically like rules that someone either say that they're true, because not everything can be actually proven, or it's a theorem that has been proved and you just need to know the result. You don't have to prove it all the time, over and over again. All right, so we want to use those laws to help us come up with simpler expressions that have fewer operations or fewer variables involved. Okay, so because they would be easier, faster for us to evaluate. So they will have a shorter form, which is of course more desirable. And so basic postulates of Boolean algebra, right? And a postulate is something that you basically have to trust. Okay, everything else can be derived, but basic postulates you just have to take as is. Okay, and some of the postulates you can try to prove, but then you would just get to another postulate that it would just be kind of recursive, so you cannot really prove it. Okay, so we have the following laws: commutative, distributive, identity, and inverse, and we are going to go over them in the next few slides. So this is identity laws, and if you look at them, they're kind of similar to our traditional algebra with numbers, right? So if I have 5 plus 0, it is 5, right? So we kind of understand what it is. So why is it called an identity? An identity is it is called because it doesn't change the value. So this 0 is identity with respect of the OR operation, right? Because a plus 0 is a in Boolean algebra, as it is in where plus is an OR, as it is in math and arithmetic, where plus is addition. Okay, it is important to remember that identity is always with respect to certain operations. So 0 is an identity for addition, and you would definitely agree that 0 is not an identity for the multiplication. Okay, so this is definitely not so. And it's the same in Boolean algebra, right? So the identity for AND is different from the identity for OR, so, and it is 1. And obviously, we discussed before the truth table of AND. So if A is 0, then the result is 0. That is the same as A. And if A is 1, then 1 and 1 is 1. So it turns out, no matter how you slice it, the result is exactly the same as A, as the operand that is unknown, right? The operand that is not a constant, the operand that is a variable, right? So that allows us to kind of, basically prove very easily, but just enumerating all possibilities that yes, this identity holds. All right, inverse laws. Again, there is a direct analogy with our arithmetic, right? So it is the value that yields a 1. Okay, and a 1 can be defined differently. So for in arithmetic that would be actually 0, and if we want multiplicative inverse, right, then it is defined like that. So 5 and 1/5 are multiplicative inverses of each other. 5 and -5 are additive inverses of each other. Okay, so it's the same here. So A or not A is always 1, and A and not A is always 0. So again, we proved those inverse laws here, right? But just enumerating values. X2 and X3 were our examples of that. All right. So commutative laws, and we're not going to prove it here. Again, you can easily prove it by just enumerating all possibilities for A and B, by just essentially building the truth table of their left-hand side and right-hand side. And when you build the truth tables and compare, so how do you build a truth table? You just say A, B, and F1, where F1 is, let's say this is F1. Okay, and then do your 0, 0, 0, 1, 1, 0, 1, 1, compute F in each of the cases, and then do the same for F2, B, A, F2, do the exact same thing here, compute F2, and then compare these two truth tables. And if their two truth tables are exactly the same, so every line matches between these two truth tables, it means they implement the same function. It means that F1 is actually the same function as F2. So the important thing here is to see that, well, it is the same function, but they are different formulas. So this, the left-hand side and the right-hand side are not the same formula. The formula is different, right? A plus B is not the same formula as B plus A, right? Because we swapped the operands, but it turns out that our function doesn't change if we swap the operands of an OR, and that means it's the same function, and that's how we can demonstrate that commutative law with respect to OR holds. Right. So later on homework assignments, on tests, you might be asked, how many formulas can we have for the same Boolean function? And the answer in general is many. Right. We can have multiple ways of writing their formula for the same Boolean function. So their functions are the same if you build the truth tables and the truth tables agree in absolutely every row. That's what defines the function, right? And if truth tables are the same, the functions are the same. Okay? And then we can do the same kind of thing for and commutative law also holds for and. You can swap the operands of and it's not going to change. The function is going to be the same function. All right, so distributive laws. So they are on one hand kind of similar to our traditional algebra, but please be very careful, because not all analogies can be carried over from your traditional middle school algebra into Boolean laws. So do not assume that if a certain formula, if a certain law exists in our traditional middle school algebra, it will be true for the Boolean algebra. Okay, so please refer to these slides as a set of laws that we can just take as granted, right? In any of their assignments or on the exam, you can just use those laws, right? We might ask you to actually tell us which law you use, right? But unless we specifically ask you to prove something, you don't have to prove the laws that appear on those slides. You can just take them for granted, right? So you can just say, oh, I'm making this step in my transformation by applying the distributive law, and that would be sufficient, right? You don't have to prove that the distributive law holds. Do you have to remember the name of the law? Yes, we, at least on the homework, we will ask you to, well, to tell us as a proof that your transformation is correct, which law you are applying. Okay, because then it makes it very easy for us to check, oh, you applied the law that actually does not exist in Boolean algebra. Okay. All right, so those are distributive laws with, for or with respect to and vice versa with for and with respect to or. There are other identities that can be derived from these basic postulates. So laws of ones and zeros, associative laws, and De Morgan's law or De Morgan's theorem. So this one is a very common. This one is widely used. It's very very common. So definitely, well, others are useful as well, but like the laws of ones and zeros are pretty much straightforward. But De Morgan's theorem, as an exercise, try to prove it. Okay, I'm sure you can do that. We're not going to ask you to do this on in this class. All right, so I don't know if you do this in Fox or not, but just for fun and just to test your abilities, you can try proving the De Morgan's theorem yourself. But okay, so let's go over those things. Right, so those are derived. So unlike postulates, you can actually easily prove those. Okay, you don't have to just to trust. You can actually prove it based on the postulates. So a or 1 is 1, law of ones. A and 0 is 0, law of zeros, pretty straightforward. And associative laws. Okay, so note that distributive laws are up there with the postulates, but associativity laws or associative laws are here that are like derived laws. And so basically it means that you can change the order in which you perform the same operation easily. So instead of first doing B or C and then doing A or the result, you can first do A or B and then take this result and OR it with C. And similarly for and for conjunction. Okay. Note that associative laws, you have the same operation here and here. You said you have the same operation, right? If it's not the same operation, then you cannot apply associative laws. So then you have to check if it falls under distributive laws, and if it does not, then you either have to prove a new law or you just have to do something else. All right, and De Morgan's theorems or De Morgan's laws. So they help us deal with negation, and basically it means that if we have an expression that is an OR and the result of the OR is negated, we can replace OR with an AND, but we have to negate each of the arguments. Okay, so instead of doing A or B and then negating the result, we can compute the same function if we negate each of the operands A and B separately and then AND the result. And then the second De Morgan's rule is see how beautiful it is. See how it kind of almost a reflection of the De Morgan's theorem 1 for on or, and the second one for and is very similar. It's just if we have A and B negated, we can just negate A, negate B, and take the or. So they are beautiful. Okay. All right. Oh, and we have another pop quiz. So let me turn it on. And yeah, the annotation that I used on submitting, so was, I think I used the tilde. So this is something we discussed, right? A tilde is negation. So it's similar to this over bar. All right. And where do I have my poll number 2? Hopefully that's the right poll, but please check. Should be open now. All right, so there are other operators. So Boolean algebra is defined over this 3, basic operators, which we call a functionally complete set or basis. So and, or, and not, it's not the only basis. We can later on. Oh, it's actually here on. No, it's not on this slide, but we will talk about it briefly. So it's not the only functionally complete set. There are others, but this is one of the most common: and, or, and not. And that means that you can define any Boolean function using just these three operations. So we don't really need all 16 that exist out there for two operands. You can just use these three. And there are other useful operators which are combinations of the three that we discussed. Some of them are not combinations. So if we look at them, nor is not or, okay, and that's why it's called nor. And basically that means that you or and then you negate. So this is nor. Okay, so you can say A nor B, and it would be the same thing as this. Okay, so nor basically means take an or and then negate the result. Okay, and so obviously their effect would be nor returns a 0 if either operand is a 1, right? Because or would return 1 if either operand is a 1, and when we negate 1, we get exactly this 0. And NAND is also a very common operation, so this is NAND, A, NAND, B. Okay, so they are the same. And yeah, as far as I know, there are no standard symbols for NAND and OR, so you can just write them like that if you want. Okay, so obviously NAND is 0 only if both operands are 1, because that's when AND returns 1. And if you negate that 1, you get a 0, which is exactly NAND. And XOR is 1 if the operands are different, so it's exclusive OR that we already discussed. And yeah, so nor or NAND. So each of them by itself is a functionally complete set. So try to think about why. So basically, what this statement says is nor is sufficient to represent any Boolean function. Okay, it's a pretty strong statement, right? So we're saying, well, we might need to have and, or, and not. So these three have to go together to be a functionally complete set, right? And by itself cannot be used to express any Boolean function. We need to have all three. But then we say nor by itself or NAND by itself can be used to express any Boolean function. So we only need this one operation, which each of them would be a functionally complete set. Okay, so think about why is that? Okay, and think, I can give you a hint. You might find De Morgan's theorem useful and see how you can maybe use just this one operation to actually perform and, or, and not. So you can kind of show that these two sets, this one, and nor, are actually kind of equivalent in their expressive power, in their number of in the fact that you can implement any function using them. All right, so they are both functionally complete sets. Can you represent any of the original three with nor and NAND? Yes, that is exactly the hint that I gave you. Okay, so you can. All right, and the key to that is De Morgan's theorem. All right, so again, we're not going to be asking you for to prove that, but think about it, because it would probably help you understand Boolean algebra better. All right, so far we had Boolean algebra, which was pretty straightforward. But now we, of course, make things more complicated. Now we say we can have functions, and it's like your life in middle school all over again, right? First, they tell you, oh, things are so simple. You just have those letters that stand for numbers, and that's it. And they throw in a few rules at you that you can apply when you're simplifying expressions, and then they say, oh, but now we have functions, those mappings between two sets of variables, and that's where things get a lot more complicated, because now you can have plots and graphs and all that business. All right, so the same kind of stuff exists in Boolean algebra, and we have functions that operate on Boolean variables, and of course the result of their function is a Boolean value itself. So we already discussed it when I was showing this domain and range, and the notation we use the same as in our traditional middle school algebra. So we have f to denote some function, and in parentheses we write arguments. So this is a function of two arguments, a and b, and this is how the function is defined. So this is the rule for computing this function. Okay. All right. So we also can define a Boolean function using just their value of the function for each of their combinations of inputs. Okay. So there are different ways to represent a function. One is use their formula, algebraic operations. So like here we say it's a or b, and the other one is just to list all values. So here's a and b and f, and we have to list all their combinations, and then we have to define our function by just putting the correct value, right? So, and the function I defined here, you can see that it is actually a plus b. Okay, but we can define other functions, right? So as we already discussed, how many different functions we could actually build for two Boolean operands, right? It would be 16. All right, so this is something that I've just done, and this is what we call a truth table, right? A very easy way of defining function. If you have a relatively small number of arguments, right? If you have, two arguments, then you're only going to have 4 rows in this table. If you're going to have 5 arguments, then things get a lot more complicated, just because you're going to have 32 rows. Okay, so, and of course, the number of different functions that you can construct with 5 arguments is going to be 2 to the 2 to the 5th, right? So it's going to be a lot more different functions. All right, so here are truth tables for all our operations that we discussed so far, and so yeah, we already discussed all that. Pretty straightforward. Yeah, XOR, it's exclusive OR. It means that you can get only one thing but not 2 at the same time. So XOR is actually close to the OR in our common sense. Like, the example I think I mentioned before, like if I ask you, you want a candy or an apple, this or in a natural language means exclusive. You cannot have both. You can only have either a candy or an apple. You cannot get both from me. Okay, so, and that's the kind of or that in Boolean algebra we call XOR, exclusive or, because with a regular inclusive or, it allows you to get both a candy and an apple right here. And XOR exclusive, it says no, you cannot have both. You have to choose one or the other, only one. Yeah, or in English equals XOR in computer. Exactly, I like that. Very succinct and to the point. All right, so of course we can build truth tables for all different functions that here you see for 3 variables. Of course, our truth table has twice as many rows, so we have 8 rows, and we can just define the values for the function. So on the left we have arguments x, y, and z, all possible combination of them, and on the right we have the value of the function. Sometimes you will be told what the function is, like here they actually tell you how to compute it. There might be other times when they only give you, f. So it's some function, and you might have to look at the truth table and guess or find out how to convert this truth table to a formula, right? So you might be asked, here's the truth table, please give me the formula. So like this part, which will not be given to you, right? You will have to find it out. All right, and so now the most fun we are going to have by delving a little bit deeper into